What I'm going to talk about today is the importance of data. I had an interview recently with, I'm a roboticist, and I had an interview recently with a magazine that wanted to talk about how blockchain is going to improve logistics. And I don't know why he chose me, and I told him, I said, I don't know anything about blockchain, but I can tell you about robotics. And all through the interview, he kept saying, yes, but how is blockchain going to disrupt logistics? And I said, I don't know anything about blockchain, but I'm going to talk about robotics. So I'll repeat that to you today. I don't know anything about blockchain, but I'm going to talk to you about robotics. And the main point I want you to take away, just very quickly, I'm Chief Innovation Officer at Vecna Robotics. I'm also founder and president of Massrobotics. Massrobotics is an industry organization here that has over 190 robotics companies in the greater Boston area. Vecna Robotics, is there a laser pointer on this? I guess there's not. Established about 20 years ago, and one of the things that I really like to point out is that we're very committed to this idea of giving back to the world. So we've done over 170,000 hours of community service, which for a small company of our size, we're quite proud of. Some of the areas of expertise, robotics, of course, is the common thread of all of these. And we have a very wide fleet of robots. This is one of the things that makes us unique in the industry as opposed to having one type of robot. We've developed software that allows AI with a lot of data to drive any number of platforms. So we run the same software, whether it's a big forklift or a truck or a tractor, all the way down to these little very inexpensive robots. They all run the same software. And again, the key point you'll see there is the data. As we know, the world is changing very, very quickly now. The rate of change in technology continues to accelerate. Of course, we all understand the reason for this. It's largely driven by data, knowledge. The more knowledge you have, the faster you can build new things. And so it's this virtuous feedback loop. The more technology we have, the faster we can create new technology. But this is creating both opportunities and challenges, of course. We talk about the Amazon effect, how everybody wants exactly what they want. They want it to show up within an hour. And if they don't like it, they want to be able to send it back. This is an unreasonable expectation. Amazon has created an unreasonable consumer expectation, yet it is what it is, and we all have to deal with it. Competitors have to figure out how they're going to compete in this environment. Answer, of course, is data. So the physical world has things that are manufactured, things that move, and things that need maintenance. So when we get out of the virtual world, the Facebook and all of that, you get into the real world, you realize there are these 3 M's: manufacture, move, maintain. And the short version of our future is all of this will be done by robots in the future. There's going to be exceptions to that, obviously, but you can think of very few physical systems that are not great candidates for being automated by robotics in the future. And so what that ultimately means is that the economies, the organizations, the governments who have invested most in automation are going to have a huge advantage over those that haven't, because the economies of scale that this allows. And there's a lot of fear around this right now. Unfortunately, every other conversation I have about this, at least, is about, oh, but robots are taking jobs. And we're going to see this widening gap between the rich and the poor, and then of course the extreme ones will say, and AI is going to take over the world, and we're all going to die. Not going to happen. Don't worry about that. It's very easy to buy into a Hollywood view of what AI is and what the risks are to the human race. Now, I'm not saying that human beings won't use technology for evil. They always have, they always will. But on the flip side, I think as a species, we have the opportunity to also use technology to help combat that, as we always have and we always will. Who ultimately will win? Who knows? Go see a great movie. There are lots of them on that. But the point here is huge, huge, huge opportunities and huge risks for those who don't take advantage of technology. Key to making all this work is data. So, one of the interesting things that I'll just point out is this safety issue. This has been in the news a lot recently, and the issue is that we expect more from technology than we expect from humans. So, there's, I'm not going to talk about on-highway, Uber or Tesla issues. What I'm talking about is in warehouse. In warehouse, there's thousands and thousands of accidents a year. People getting run over by forklifts and getting smashed between a rack and a material handling pallet jack or something like that. And what we've already found, for instance, when we deployed our fleet at FedEx, that the number of accidents basically went to zero. They used to have a lot of problems. They have stanchions. Stanchions are those metal poles that they put to protect equipment and that type of thing. And they used to have to replace these stanchions, at least one stanchion, they said, every few days because somebody would run into it with a big piece of equipment. And since they installed our robots, they've had to replace zero of those. And of course, the bigger issue, of course, is not stanchions, but damage to their equipment, damage to products that you're trying to get from Amazon to your house, and most importantly, of course, injuries to staff. And so those numbers go way down. But that's not enough because we expect technology to be perfect. So that's important to keep in mind that technology is absolutely increasing safety. But it'll never be enough, and we need to continue to make that a top priority. And again, the way we do that is machine learning and lots of data. And so I'm going to talk a little bit about this idea of IIoT, Industrial Internet of Things. The whole point here is to close that feedback loop. Right? For years and years, people have built robots, industrial robots that are record and play back, or weeks or months of programming to get that, gravity's on, to get that perfect welding bead, right? And then once they get that thing right, it just does the exact same motion every time. That's not what I'm talking about, of course. What I'm talking about is sense, think, and act. This loop where you have to actually sense the world as it is at the moment, make a plan, and then actuate your robot to do something. In that paradigm, what happens is you design a robot to operate in a specific environment, you write all the code, and then you deploy it. And that robot doesn't change. It doesn't adapt over time. That was good, that was okay, but we have much better options now. And with the concept of Industrial Internet of Things, right, the idea is there's data out there. And we should be sucking that data in and doing something with it. We bring that data in, and we can learn from it. We can obviously monitor how are things going, are the issues that need to be addressed. But ideally, then we're feeding that into machine learning that can help the robot not only not get worse, but help the robot get better in the environment. So intelligent machinery networked into intelligent systems, data. So now we can make more intelligent decisions and optimize, continually optimize how our robotic fleet is working in the real world. And this is really important because the world is not a static place. That environment that you design that robot for is changing, and it's changing every day. And sometimes, because of how technology was in the past, they go to extreme measures to try and make sure that the world doesn't change. To compete, we have to change. To keep up, we have to evolve, and we have to evolve faster than ever before. But if your technology can't keep up, then not going to be successful. So what I'm just doing is stroking the egos of all the data scientists out here and saying you're the most important piece in this equation going forward. So I'll probably just skip this in the interest of time. This talk actually was an hour talk, and I've got a half an hour, so I'm going to slide through a couple of them fairly quickly. And I kind of just talked about this. Instead of the idea of conventional, where there's no intelligence, or instrumented, we're really getting to smart and fully autonomous. We talk about autonomous systems again, and there's no good definition, but it has been in the past something that just moves without people intervening. I like to redefine autonomous to say something that is intelligent and learning over time, so that it's not just playing back previously programmed capabilities or activities, but it's actually optimizing itself over time. And this happens at two levels. It happens both at the individual robot level. So an individual robot may need to find a path through a facility. It has to deliver something from, let's say, loading dock A to unload bank C. And because these are complex environments, there's human-operated equipment running around, those patterns may change over time. So that robot has to get smarter. And it does that through a number of approaches. In the simplest version, it keeps track of how long it takes it to get from location A to B to C to D, and then can learn that, on Fridays around noon, this particular path seems to be really crowded because Team X is having their lunch break there, so it takes this other route. And again, that's a very simple example, but it shows the robot learning and making a decision rather than a programmer observing something and explicitly programming it in. I talked a little bit about safety, and it's probably a good time to just mention that there is a conflict between safety and data-based machine learning approaches, particularly when we start talking about big, heavy equipment. So our navigation technology on our robots is heavily focused on this type of warehouse equipment. We automate shuttles for people to ride in as well, but not on highway. We don't do the highway stuff. We're leaving those landmines for others to clear. But the safety issue is important because what you find is that in certain situations where you have a robot or a piece of equipment that can do harm, that can cause death, there's oftentimes requirements, as there should be, for third-party safety certification. And a third-party safety certification requires a very set approach to how you engineer those systems, and nowhere in there is there the possibility of machine learning and data mining, or data, right? Because that is not an approach that can be precisely analyzed to determine that it is inherently safe. Machine learning data won't solve all the problems in the world, but we believe it's a very important piece of this. And so the way we've done that is we've built a very structured safety architecture that has a variety of layers. And at the top layer, that's where all the intelligence is. That's sort of like the main brain, and all of your high-level reasoning is going on there. But then as you go back down, we get to this lowest level system that has very few lines of code. And the idea is that because it has very few lines of code and it's validated in a NASA style, when you're sending a rover to Mars and your opportunity to update that software is very, very limited, you want to make sure that software doesn't have bugs in it. And so you go over it thousands and thousands of times. So same thing with our software at the safety level. We make sure that that software down here in the brainstem area is rock solid, and a third party can't come in and read those lines of code and make sure that it is a safe approach. So that'll have to be there at some layer. And I was actually quite surprised in dealing with some of our colleagues in the autonomous driving on highway that at least currently they don't have a concept of that. They sort of build this monolithic system that's driving the vehicle. So I think that's going to have to change, obviously. But just very quickly, one of the things we're doing is rolling out these robots across manufacturing, retail, shipping. And we've found that there's these 6 really important steps to making things work. And I'm just going to highlight the ones that are particularly relevant to data science. So number 1 is understand your metrics. And this is a big mistake that is often made. Particularly, there's so much hype around robotics right now. You might have a CEO that says, we need to invest in robotics. Go out and do a robotics project, or go buy some robots. Bad approach. You really need to understand what your goals are, what you're going to accomplish. Set your metrics. Now, of course, metrics like cost and throughput efficiency are always those ones they say, I want to build this system and it's going to handle 1,000 cases per minute and it's going to be amazing. And sometimes people forget things like flexibility, robustness, and scalability. There's this thing called peak. Thanks to all of you buying things last minute on Amazon. Peak for a warehouse can often be 5 times their normal operating level. What that means is that 5 times the packages is trying to go through that facility during peak as the rest of the year. And if you're not planning for that up front, of course, you find yourself in a horrible situation where you've built this theoretically high throughput system, but it actually doesn't handle peak efficiently, and you run into big trouble. So flexibility, robustness, scalability, these are very important things. You can only get these with good data. You can only get these with good simulation and data analysis and that type of thing. Otherwise, you don't know what you're doing. So simulation is all about data, of course, right? What we do is we build very robust models of the world, both at 2 levels. Discrete event simulation is sort of this enterprise-wide, the entire system working together. But then we also take it all the way down to the full physics-based simulation, where we're simulating the friction between the wheels and the floors. And it's more like the Matrix at that level, right? We actually trick the robots into thinking they're in the real world. They're not in the real world, they're in the Matrix. And then we just throw all kinds of crazy things at them. We throw, noisy sensor data, we throw obstacles, we throw peak volumes and all of that, and see how the system does. And this is good for 2 things. Again, it helps us to improve the robot navigation algorithms and that type of thing, but it also helps us to choose what the best design is for the overall system. What robots do we use? Do we use big tuggers that are carrying pallets of things? Do we break them down onto the individual small robots? There are way too many variables for a human brain, no matter how experienced, to just magically come up with the right solution. So with simulation, we're able to create a realistic environment and then just try thousands and thousands of scenarios. Again, this is all about data. We can't do that without data. And ideally, what we're using is historical data from orders and shoving that data through, throwing a lot of Monte Carlo generated data in there. And then when we actually go to deploy the system, there's a high level of confidence that it's actually going to work. Obviously, a failed scenario in a simulation costs you a few hundred, maybe a few $1,000s. A failed deployment in the real world could cost you millions of dollars. Okay, so it's not as relevant, but very, very important. I've heard lots of horror stories about robotics companies trying to deploy technology and the staff literally sabotaging the equipment because they're afraid robots are going to take their jobs. We have never seen a scenario to date where the robot's taking people's jobs. What the robot does is empower their productivity, allow them to be more productive, allow them to spend their time more effectively and get more done. There are massive labor shortages in material handling industry, and many of our customers have over 300% turnover. That means they simply cannot hold on to staff. Why? Well, they're working, to constantly pay more and more and more, but what they find is no matter how much they pay, people do not want these jobs. These are not jobs for human beings. So, all of the rhetoric you'll hear about robots taking humans' jobs, I would argue that robots are an easy target, but other type of technology, of course, has had far greater impacts in that area. Switchboard operators, for example, used to be a huge industry for switchboard operators. Along came modern electronics and allowed us to have an automatic switchboard, and those jobs went away. I don't think any of us are complaining about that right now. But the more interesting point is if you tried to manage human communications today with switchboard operators, it would take many, many times the total population of the Earth in order to do it, meaning it's just not possible. So we always have to take that into account. What are the benefits we're going to get with the technology? It changes the way humans live. That's always going to happen. And let's see if we can make sure that that turns out to get us all to a good place. I kind of talked about this already. Smart navigation. It used to be that when you deploy robots, you spend a lot of time cutting holes in the floor so you could lay magnetic tape so that the robots would know where to go. You don't have to do that anymore. You take the robots out of their crate, you show them around, just like you'd show a new employee around, and then you let them do their work. Now this is a really key one, the core task manager. The core task manager is the system that overlooks all of the technology in the enterprise. It's sort of that grandmaster chess player that's sitting up there looking at the board and saying, all right, here are all the moves I can make with all the pieces I have, all the resources, the robots, the equipment, the humans. Here are my assets, here are my agents. And then over here, here's the list of all the things I have to get done in the next 4 hours, or 6 hours, or 2 hours, or 5 minutes. And so then what it does is essentially forward simulates, just like a computer program to play chess, and it tries lots of different options. What if I move this piece here? What if I move this piece here? What if I do this? What if I have a robot take this delivery? What if I assign a human to take this delivery? And it finds the best approach to accomplish the goals based on the metrics, based on your fitness function, right? The values that you have prioritized. And so, again, this is all about the data. You need to know where everything is, telling them what that next thing they can do that's going to help the organization get the orders out the door as quickly as possible. And that's how we get the smart optimization. The system constantly looking at how can I get the most done with the resources I have available to me. This is something that happens on a very tight loop basis. How am I using my data right now at this moment to achieve the best throughput right now at this moment? But then that also goes into a bigger feedback loop of, are there changes I need to make to my overall system? Do I need to change the mix of robots? Do I need to change the approach to how material moves through that warehouse? Nobody can figure that stuff out in their head. That's where we need the data to do it. And quite frankly, we need better and better ways to do that effectively. And then finally, remote support. So it's unrealistic to think that robots are going to be smarter than humans. They're different, right? We're smart in different ways. But humans need supervision. Humans need to be able to ask questions of somebody. And robots, particularly as we expect more and more from them, need the same ability. So a lot of organizations put robots out there in the sort of prior model, and the robots do what they do. And if the robot runs into a problem that its programming doesn't handle, it basically goes brain dead, right? It just stops. And oftentimes it's very inconvenient because someone has to then realize that the robot hasn't brought the package to where it needs to be, walk out onto the floor and find that robot, and then, if it was based on Windows, probably reboot it or whatever. But the reality is that human workers need help all the time too. That's why human workers have supervisors, because they may be faced with a situation they don't know how to handle. And so they get their hand up, or they get on their walkie-talkie or whatever, and they call their supervisor and say, hey, there's a pile of stretch wrap here on the floor, and I don't know what to do with it. What should I do? Same thing with the robots. So what we've done is given our robots enough intelligence to, one, know when they need help. And that, maybe sounds trivial, but there's a lot of nuance there. How does the robot know when it needs help? And then two, when they know they need help, we've given them ability to phone home to our remote assist center where they can ask for that help from somebody who that has the tools to help them. And that remote assist person will basically log on to the robot, assess, has a view of all the sensors, historical data, that type of thing, and can see what's going on. And oftentimes within less than 90 seconds, they have assessed the situation and given the robot a directive that allows the robot to progress towards its goal. And that's an approach that has allowed us to, for instance, win a significant amount of business at FedEx, where your package has to get through. It has to get through. And having a robot that stops and brings their operations to a halt just isn't an option. So these are the 6 steps and that we found are very useful. And the main point I wanted to make is that all the way through it, it's all about data. It's about access to the data. It's about making sure that you understand the data, and then it's using that data in the most efficient way possible to achieve both short-term optimization and then long-term optimization. So I wanted to open up for any questions, comments, objections. Yeah?
I had a question about your core task manager. Is there
Yeah, so that's a great question. Right now, our core task manager is sort of per facility. But I think that's a great point, that it's ultimately probably going to be a multi-layer, all the way up to the main enterprise core task manager. They're actually trying to come up with a better name than core task manager now that they're starting to market it too. But calling it like Nerve or Symphony or something like that, some Silicon Valley type name. But yeah, so that's a great point. Right now, it just focuses on a deployment with a set of robots. Yeah, you had a question?
Just broadly, if you could speak a little bit about how the security, how is it absorbed in the process, both from the beginning and just sort of the relationship between that.
Security? Yeah, that's a great point. The question was, how is security involved with all this? And it's key. One of the things that we're very fortunate at Vecna is that we have been doing military and healthcare work and payment card industry work for many, many years. So, security is a key part of everything we do. We're constantly being audited by the military, et cetera. But yes, it's very important. And we of course look to the software security industry for the solutions for that. But if somebody gets in and takes control of your infrastructure, you're going to be not able to keep up and compete. So I would just say that that's a very important underlying foundation of everything that happens. But of course, in this world of connected devices, that gets more and more complicated. So yes.
Regarding your remote support of the software, how do you deliver your bug fix or even software upgrades to all your robots out in the field?
Yeah, so the question was, how do you upgrade? The answer is that when we work pretty hard to make sure that there are regular updates going out, because this continual learning that we're getting, we're constantly enhancing the system. And typically what we'll do is we'll roll out to one individual bot in the environment remotely, and give that a burn-in period to see if it's a good release, and then we will just push out to all the robots in that same facility.
How do you push out? Like, do you remote deliver the software?
Yeah, so they go through a process of bringing the robot down, downloading the appropriate files, and then basically bringing the robot back up in a controlled way. Yep, question?
Yeah, so trying to ask your vision why, because the industry is kind of tending to grow a lot of monopolies, right? Such as Google, nobody can catch up with them, right? And Facebook, social media,
Yeah.
and robot and artificial intelligence. Do you see, say, certain companies group so much data and become the next monopoly, or
Yeah.
super artificial intelligence, all the many companies collaborate and be better and better?
Yeah, it's a great question. I mean, monopolies are a challenge. It's a big question, right? When you concentrate too much power, it creates all kinds of non-ideal situations. Data, of course, is the key. I was listening to Gil Pratt, a friend of mine. He was a professor at MIT, and he works at Toyota Research Institute now. And the point he was making very strongly is it's all about the data. And whoever controls the data ultimately wins. So I don't know if I have any great answers to that question, but I think it's an insightful point. Access to data, control of data is probably one of the big questions we have going forward into our ability to compete fairly in the world and make sure that things don't get too far out of whack. Yes.
Hi, we have the mic.
Inputs you're using to learn or interested in learning from? I mean, are you at the level of vision stuff, or is there sort of infrared or?
Oh, yeah, sensors?
Yeah, what kind of inputs?
Yeah, so we've developed a very unique system in what I would call sensor fusion vision-guided robotics. And so what I mean by that is we developed something called the Autonomy Kit. The Autonomy Kit is our, we put over $60 million worth of R&D into building this brain that can drive anything, basically. So it's both sensor agnostic and platform agnostic. By platform agnostic, I mean through some very straightforward configuration and then learning, it figures out how to drive any different platform, whether it's an Ackerman steering or a differential drive or a powered caster, or whatever it is, we can configure it and then it learns how to drive that platform. In terms of sensors, going back to the matrix analogy, the robot AI operates in this virtual world. And we use the appropriate sensors for the situation to populate that virtual world. So we're not hard-coded to any particular sensor. So we use LiDAR, we use time of flight, we use structured light, we use infrared, IR, visible light, stereo. We use Wi-Fi, we use Bluetooth, we use fiducials. We can print out a barcode and put it on the wall. The robot can snap a picture and then compare it to its picture database and say, oh, I know where this picture was taken and it's similar to that one, so I know that I'm in this conference room. And so we use this whole, again, sort of data-driven approach for, there are two things you need to do. You need to localize, and then you need to navigate. Localization is all about realizing where you are. Navigation is all about knowing which direction you need to drive in and avoiding obstacles. And there's no one perfect sensor for that. So the ability to use data from lots of different sensors, register that sensor data together in an intelligent way is really key. And unfortunately, not many organizations are doing this effectively yet, because it's way easier. For instance, ROS, the robot operating system, primarily localizes with a LiDAR and scan matching. And what that means is it'll use the LiDAR to get a 2D sweep of the world, and then it'll compare that to its previously saved maps and try and find where it gets the best registration of that 2D sweep. It's okay. It's fast computationally, which is good, but it's not necessarily the most robust approach. Are we done?
Yeah.
All right. Thank you very much.